This is Lecture 29. Last time, we talked about the new institutions of natural science that began emerging in the third and fourth decades of the 19th century. And we noted that, along with them, the scientist emerged as a recognizable social identity. There was now someone who was a practitioner of natural science. In the years leading up to the middle of the century, people slowly began to become familiar with the presence of scientists in their midst, people who spoke with authority about nature and about the proper method to use when probing nature for new truths. During this same period of time, a number of celebrated events occurred in natural science. Some of them we've already learned about, the sensation over Chambers' book on the vestiges of the natural history of creation, for example. There were also developments from the physical sciences that occurred as well, and we'll look into some of those that captured the public's attention in future lectures. But there was another development that didn't receive much attention in the press, even though it was a crucial result for natural science itself. It had to do with the establishment of a law of conservation. Now, conservation is a notion that crops up frequently in natural science. In fact, today's story is about one of the more famous cases of a conservation law in the history of science. We know it as the conservation of energy. That phrase, of course, has come to mean something very specific to us in the 21st century. We use it to refer to saving energy as opposed to wasting it. We want to be frugal in our consumption of energy. We want to conserve energy because we know that at present we don't have an unlimited supply of it to address our ever-increasing needs. But I'm using the word conservation today as it frequently occurs in natural science, in the sense of a law of nature in which some fundamental quantity can't be used up. We encounter things in science that we say can't be created or destroyed, although they can be changed from one form to another. But identifying exactly what those things are can be tricky business. In today's story, for example, we'll see that even after scientists concluded that they'd established a new conservation law, they weren't all that sure what it was they'd shown was being conserved. Our focus in this lecture deals with the development about what would eventually be called energy. It's an interesting episode because it illustrates something I mentioned way back in Lecture 1 about the pitfalls of writing the history of science. I mentioned then that especially where ideas about natural science are concerned, it's extremely easy to take perspectives we've formed in the present about science, and we take them with us as we go back in time to investigate the historical development of science. And I suggested that historians regard this as a no-no. We should avoid imposing the way we look at things in the present onto the past when they don't belong there. In particular, we shouldn't assume that what we understand natural science to be in the 21st century fits past situations. Now, the story I'm about to tell you contains an irony that makes this point very well. And the reason it's an irony is because the guilty party who imposes an assumption onto the development of energy conservation in the 1840s and 1850s turns out to be none other than Thomas Kuhn, the very person whose eloquent warning against doing this kind of thing I cited in Lecture 1. Now, I hardly mean to accuse Kuhn of hypocrisy, of saying, don't do this when writing history of science and then going and doing it himself. It's not a question of being hypocritical. Recall that in that first lecture, I also admitted that it's virtually impossible for us not to bring some ideas from the present with us as we go back to the past. They're too embedded in our way of thinking to get rid of completely. I suggested that our job as we try to understand the past was twofold. One, to try our best to avoid smuggling present-day notions into our historical accounts. And two, to point out examples of this kind of thing when we do recognize them. Well, let me explain why I think Kuhn unintentionally has done what he himself warned us against. Some time ago now, Kuhn wrote an essay on this period entitled Energy Conservation as an Example of Simultaneous Discovery. In it, he tried to explain why a number of individuals, up to 12, were moving toward the general conclusion of energy conservation right around the same period of time. Now, Kuhn was careful to note the piecemeal contributions of different individuals. Nobody seemed to put it all together. But Kuhn's central concern clearly revolved around the idea that energy conservation was discovered by several different people at the same time. That was the basic point he was making. Now, what Kuhn was assuming in his essay was that this narrative was a matter of discovery. That is, he assumed that energy conservation was something that had been discovered in the 1840s. That certainly sounds harmless enough. We all know about the law of energy conservation, and it's reasonable to assume that somebody must have discovered it. But as we will see, it's much more likely that had we been alive in these years, we wouldn't have observed the simultaneous discovery of this concept in the way Kuhn portrayed it. The more we learn about the details of those involved, the more historians have become convinced that it was an episode that's not best depicted as a story of discovery. Well, what then? How should we understand what happened? Well, many historians of science today depict this episode as a protracted struggle to understand nature that only gradually produced a consensus. These historians prefer to portray what occurred as a gradual and collective construction of a theory rather than an individual discovery. For example, many of the individual contributions to the construction of the theory didn't appear to be particularly noteworthy at the time they were introduced. So the present way of seeing things suggests it was a matter of harmonizing some very speculative ideas with some hard-to-read experimental results. Now, I want to be clear here. Of course, there have been moments of discovery in the history of science, so-called aha moments, and these have produced important results. And these results have endured. My concern is that the idea of the conservation of energy doesn't appear to have made its way into the canon of scientific results in that manner. Now, I realize I have to make good on my criticism of Kuhn here by showing you in detail what I mean in all this. And of course, I'm hardly going to imply that my portrait of the episode is the final word on the subject. But if rejecting the idea that energy conservation was something that was discovered at a particular time has merit, it's because it helps us understand that natural science sometimes develops by muddling through rather than through heroic individual discoveries. And I think that's an important lesson to learn. Well, here's how I propose to proceed in this lecture. I've chosen 3 individuals from among the 12 Kuhn identified as players. They were all under 30, and they made contributions to the construction of this eventual consensus. I won't be claiming that any one of them is primarily responsible for the idea of energy conservation, or even that all 3 are. What I'll do is to try to show you 3 individual cases of scientists grappling with a fascinating challenge. Now, in this subject, there is one of nature's forces that turns out to be of central concern, and it's heat. So I want to begin by reviewing for you what heat was thought to be in the 1830s and 1840s. In fact, there were 2 competing theories of what heat was. One, the caloric theory, assumed that heat was an inherently light substance that permeated gross material bodies. This viewpoint originated way back with Aristotle's identification of fire as one of the 4 basic elements. But the idea that heat was an imponderable substance had continued to exist. I noted in lecture 27 that Lavoisier had called this substance caloric. According to the caloric theory, heat was an inherently light substance that permeates gross material bodies. We saw in that lecture that in this conception of heat, you could associate temperature with the amount of caloric that occupied a given volume. Temperature was the density of caloric present in a body. The denser the caloric was packed in, the hotter the body got. It was a very useful theory. Say you wanted to explain why 2 bodies at different temperatures didn't remain that way. You noticed that over time, the temperature difference would even out. Well, you could easily visualize this as the flow of caloric from the hotter to the colder body until the density of caloric in each was the same. So it was a widely held understanding of heat. I noted, for example, that this was the view of heat often read into Carnot's theoretical explanation of the motive power of heat. But there was a competing theory of what heat was. In this understanding, called the mechanical theory, heat was considered a mode of the motion of the particles making up matter. This view wasn't as old as the caloric theory, but it had been entertained at least as early as the 17th century. The reason it was proposed was to account for the creation of heat through friction. That was a phenomenon that was much harder to account for in the caloric theory, as I'll explain in a second. At the turn of the century, an American named Benjamin Thompson undertook a series of experiments in Germany that involved boring cannons. What was this American doing in Europe? Well, his sympathies for the Tory cause had forced him to leave the United States. Thompson, also known as Count Rumford, focused on the extreme amounts of heat that were present in his cannon boring experiments. He concluded that the amount of heat that could be produced appeared to be inexhaustible. Rumford's conclusion was that the only way his results made sense was if heat was due to the motion of the particles in the metal. Heat would continue to appear as long as he kept agitating the particles of the cannon. Now, the reason both theories continued to exist in the 1840s was because each had strengths. I've given you examples of how each could be used to make sense of something involving heat. But each theory also had severe weaknesses. How could the caloric theory account for the apparently inexhaustible heat produced in the boring of cannons? If the heat were due to a set amount of caloric in the metal cannons that was somehow set free during the boring process, then when that caloric was all expelled, there would be no more heat set free. The temperature would drop rapidly as the boring continued. But that's not what you observed happen. But Rumford had problems too. How could he explain the transfer of the sun's heat to the earth on the assumption that it was a mode of motion of the corpuscles of gross matter? Or how could he explain why heat could be transferred through tubes in which a near vacuum existed? Where were the particles whose motion supposedly explained the heat? In these cases, it was far easier to imagine that heat crossed such distances in the form of the imponderable substance of heat. So, as the decade of the 1840s dawned, both ideas about heat were still appealed to, depending on the context. Okay, we now have an idea of the different ways that natural philosophers thought about heat in this period. One of the roots to the idea of conservation arose through a consideration of the human body's heat. It was undertaken by a young German physician named Julius Robert Mayer. Mayer signed on as the ship doctor for a Dutch expedition to the East Indies in early 1840. Now, Mayer possessed a particularly well-developed sense of curiosity. While he was in the tropics, he observed something unexpected. What happened was this: a lung infection broke out among the ship's crew. So, as the ship's physician, he had to try to treat it. And that required Mayer to perform a lot of bloodlettings. And that's when he noticed something he wasn't prepared for. He records being surprised by the uncommon redness of the venous blood he drew. It looked like that from an artery. Now, I have to tell you that his observation has been disputed. There doesn't appear to be a consensus today that venous blood drawn in the tropics is lighter in color. Be that as it may, Mayer thought it looked lighter. And he tried to explain why being in the tropics made it so. And this is what he came up with. He explained the lighter color of the venous blood by invoking a theory of animal heat that Lavoisier had originated. According to Lavoisier, animal heat results from oxidation going on in the blood. So Mayer reasoned that because the tropics are hotter than the northern climates the crew was used to, their bodies produced less heat. And that meant that less oxidation occurred in their blood. And that lessened the difference in color of the two kinds of blood. Mayer next made another inference about the heat produced by the body. This new inference resulted from some experiments he'd tried as a child. As a youngster, He'd tried to make a perpetual motion machine. And, of course, he always failed. So he'd concluded from this that mechanical motion can't be generated out of nothing. It always has to have a source. Now, as he thought about things down in the tropics, he said to himself, the body performs mechanical motions. Mechanical motion can't be generated out of nothing, so there must be a source for this motion. To answer his own question, he once again drew on Lavoisier's theory. He realized that the heat produced by the oxidation in the blood, while in part supplying the heat the body needs to keep warm, must also be related to the mechanical motions the body performs. He later expressed this insight, which he said came to him during his voyage, this way. Heat and motion or mechanical work must be converted into each other according to an invariable ratio. One more thing. In a publication of 1842, Meyer showed awareness of something not generally appreciated, namely that under the right conditions, a gas introduced into a vacuum chamber with no movable piston does not cool. Take a minute and visualize this circumstance. You have an evacuated chamber and you introduce a gas into it. How would you explain that it doesn't cool by the caloric theory? You can't. It makes no sense on the caloric theory. Why? Well, because in that approach, the temperature is correlated with the density of the caloric in the gas. And since that density is much less as the gas enters into the chamber, the temperature in the chamber would have to be lower. So what did Meyer conclude? He reasoned that when there was a fall in temperature, that is, when you had a chamber in which there was a piston that was allowed to move, in that case, it was the heat that was the source of the mechanical motion. The temperature dropped because the heat disappeared as the mechanical motion of the piston appeared. Heat became mechanical motion. Now, in claiming this, in saying that heat actually became mechanical motion, Meyer was implying that there was a mechanical equivalent of heat. That is, an amount of mechanical force that may be obtained from a certain amount of heat. Well, after Meyer came back to Germany, he put out a couple of publications containing his ideas, but he had an interesting response. His first submission to the Annals of Physics in 1841 never received the dignity of a reply. A year later, he did get a paper published. It was entitled Remarks on the Forces of Inanimate Nature. And if you read it, you encountered assertions made in a philosophical mode that many couldn't understand and didn't appreciate. Here's what I mean. Meyer was a very religious man. One way that showed itself was in his vehement opposition to what he considered godless materialism. So he refused to regard forces as properties of matter. That would attribute too much explanatory power to matter. So he argued that forces were causes. Therefore, like causes, they disappeared as the effect appeared. This was his way of saying that forces can be converted into other forces, but that force itself can't be destroyed. Okay, force can't be destroyed. Can it be created? Well, here Meyer wavered for a while. He thought perhaps God created new force where it was needed, for example, to keep the solar system from running down. But later, he eventually concluded that force was not being constantly created, so just as it could not be destroyed, it couldn't be created. Now, although Meyer's work was not greatly appreciated and not very influential, embedded in it was the idea that force was conserved. A less philosophical, more concrete argument about force conversion occurred in the experimental work of James Joule from England. He was from Manchester. He had no knowledge of Meyer's work, but he'd become convinced on his own that when mechanical motion produced heat, as it was known to do, there must be a constant ratio of the work done by the motion to the heat produced. Joule attempted to establish this conclusion through a series of experiments, which he reported to the British Association meetings beginning in 1843. He independently used the same argument that Meyer had about the free expansion of gases not producing a drop in temperature. In fact, he did demonstrations to try to convince the audience But his listeners tended not to trust the thermometers he employed in the demonstrations, so he got nowhere. Joule did a lot of experiments, but perhaps the one most well known involved a paddle wheel that was turned in an insulated bucket of water by a slowly falling weight. So as this weight descended, it caused the paddle wheel to turn in a bucket of water. Now, he carefully measured the rise in the temperature of the water and correlated it with the amount of work done by the descending weight. So now he had a precise measure of how much heat equated to the amount of mechanical work done by the falling weight. He had measured the mechanical equivalent of heat. But, as I said, lots of folks knew Joule was doing these experiments, and he'd report on them to the meetings of the British Association. But after a while, people began to turn a deaf ear to his talks. They didn't trust the measurements, and they thought of Joule as someone on a hobby horse. And then in 1847, at a British Association meeting, Joule once again was scheduled to speak. But this time, he was directed by the chair to confine himself to a short verbal description of his experiment because, Joule later recollected, his earlier experiments had not excited much attention. On this occasion, however, there was a young 23-year-old Scotsman in attendance who started asking some probing questions, and that began a long acquaintance between Joule and William Thomson, who would later be known as Lord Kelvin. We'll meet young Mr. Thomson again in Lecture 30. He'll play a major role in a subsequent phase of this story. Well, back to this phase. Now, one of the earliest announcements of the general result that was implied by Mayer's early work and by Joule's measurement of a mechanical equivalent of heat was given in Germany in July of 1847. It came from another young medical doctor, Hermann Helmholtz. Helmholtz began his medical studies in Berlin at the age of 17. Beginning in 1839, he worked in the laboratory of a well-known physiologist named Johannes Müller. There was a group of students working with Müller who were wrestling with the problem of what was called vital force. We encountered the notion of vital force back in Lecture 13 when we learned about Kielmayer. He'd identified a number of organic forces and had helped establish, that is, Kielmayer had, this new outlook that gave rise to the science of biology. The question Müller's students were asking was whether, in fact, Kielmayer and others who talked about special organic forces were right to do so. Were organic forces special, as the tradition of Kielmayer would suggest? Or were the so-called organic forces just physical forces after all? The Berlin group was convinced that organic forces were not special. They believed that there was no such thing as a separate vital force that was only present in living things and couldn't be found in inanimate nature. They thought that the actions of all allegedly vital forces could be reduced to the effects of mechanical forces acting on matter. So, young Hermann Helmholtz was part of this group of students. And for his part of the project, he was exploring how to establish the mechanical basis of so-called organic forces. In this connection, his first papers investigated how the matter of food was used to produce contractions in muscles. That was a good example of the interaction of living things with chemical and mechanical processes. So you can see how this subject brought him to inquire about the role of heat in physiological processes. In 1847, Helmholtz wrote a paper entitled On the Preservation of Force. The word Helmholtz used in his title was clearly the word for force, Kraft in German. What did Helmholtz do in this paper? Well, he began by imagining a system of bodies in which each individual body stood in a specific position relative to all the others. And all the bodies were subject to various forces acting among them. Okay, now what? Well, Helmholtz asked, what would be the case in the following scenario? Suppose the bodies moved to different positions because of the forces acting on them, and then suppose they subsequently were moved back to their original positions. Helmholtz argued that any work gained by the first motions would be exactly lost by the movements back to the original position. If this was not the case, he said, if when you restored the original positions, you had some mechanical force left over, then you'd gain something for nothing. You could exploit such a situation to create a perpetual motion machine, but that was something he rejected out of hand. Let me give you a simplified example to illustrate what he's saying here. Take one piece of matter that's attracted to another. Say the case of an object that falls to the earth. After it falls, if we raise it back to the height from which it fell, any gain from its fall, any work we got it to do by falling, will have to be expended to replace it. Now, Helmholtz's analysis was general. It wasn't limited to a single cause of motion, as in the example I just gave. He said you could include many causes of motion acting simultaneously. We need to unpack something else here that isn't all that obvious from what I've said so far. Helmholtz referred to two different kinds of force in his analysis, each of which should be converted into the other, or could be converted into the other. One he called the tensive force because it's exerted without motion resulting. In our simple example, this is the gravitational force acting on the weight before it's allowed to fall. It's there, but it doesn't produce motion. That's one kind of force. The other was living force. Yes, it's the same force we got from our old friend Leibniz. He called it vis viva. And so did Helmholtz. This was the force the weight exerted when it was moving. It was the force the weight exerted by virtue of being in motion. Well, for a system of bodies, you have three possibilities. At any time, the individual bodies in the system either have only tensive force and no living force, or they have only living force and no tensive force, or they have some combination of part tensive and part living forces. That's it. That's the only possibilities there are. What Helmholtz was saying was that there was something here that stayed the same regardless of which of those possibilities pertained. And that was the sum of the two kinds of force, the sum of the tensive and living forces. When you move from one combination of tensive and living forces to a different one, it's the sum that stays constant. Now, Helmholtz was a smart guy, so he expressed this conclusion in mathematical form, and that just underscored its generality. The sum of tensive force plus living force is always a constant. The sum of forces that could produce motion if allowed to, plus the forces that are already present in things that are moving, this sum is constant. Now, this is a very general result. I know it went past you a little quickly, and it might not all have sunk in. Don't worry about that, and don't feel bad. If that was your experience as I talked about all this, you're in good company. It didn't sink in 1847 either. Although Helmholtz had arrived at a very general result, there was not yet clarity about exactly what it was that was conserved. To what in nature did all this sum of tensive force and living force correlate? As I said earlier, the word Helmholtz used here was force. The modern idea of energy was implicit in what Helmholtz concluded about force, but it would take a while before anyone would talk about energy. In fact, when Helmholtz submitted his paper to be published, guess what? It was rejected by the same physics journal that had rejected Mayer's paper earlier. In both cases, the editor regarded these ideas as overly philosophical and speculative. I can hear the editor now. The conservation of what? Now, I hope you can see why we should avoid characterizing these developments, which were obviously part of the collective construction of what later would be called the conservation of energy, as simultaneous discoveries of this fundamental principle. In retrospect, people usually go back to Helmholtz's 1847 paper as the place where the conservation of energy was first articulated. But as we've seen, that's not exactly how it was presented there, nor was it how it was received at the time. Clarification in the matter, clarification about what exactly it was that was conserved, would come about only as another aspect of the fascinating subject of force and energy emerged. And that was the realization that while force could not be created or destroyed, it might become unavailable. And when physicists came to that conclusion, it had disturbing implications about the end of the universe that were at variance with traditional Western religious ideas about the end of time. And we'll turn to that intriguing development in our next lecture.